in a building, and we need it because GPS can't be used indoors. Indoor environments can be really hard to navigate because of how complex and diverse they are. But we do need indoor localization because it can be used with blind and visually impaired people to find their way in indoor places such as homes, restaurants, and malls. Indoor localization can also be used in many other scenarios, such as keeping track of inventory in stores or to locate dangerous areas in emergency situations. Next, I'll talk about the existing indoor localization methods. The first one is Bluetooth Low Energy beacons, and this allows us to localize people based on the strength of the Bluetooth signal. The next one is magnetic sensors, which work in a similar fashion, and however, they can't be used with wooden architecture. Next, emitting Wi-Fi signals can allow devices to determine how strong or weak the signal is and also localize the person. Lastly, we have inertial sensing, which tracks the acceleration and speed of an object to find its location in a room. However, all of these come with several cons, and these are that they need previous built-in infrastructures and they also need a prior mapping process. ARKit is a framework that uses visual inertial odometry, and it can create an accurate representation of the real world around a user. Visual inertial odometry is a process of estimating the state of a user by usually using the input of cameras and inertial sensors. ARKit can also accurately track how a device moves in space. The pros of using ARKit is that it's widely accessible as it's available on all iPhones, and the new iPhone Pros are also equipped with LiDAR, which is more helpful when using it. Next, I'll talk about some of the methods that we use in our research. To start off, our guiding question was, can we do indoor localization without a pre-mapping process? The solution that we proposed is a two-step localization system. The first part of it is a prior estimation method, and all we need from this is a coarse estimation of possible locations a user can be. The second part is matching plans with the floor plan and ARKit to help us refine our localization more accurately. Okay, now I'll try to have you imagine our solution for a second. First, imagine you're lost inside a building and you aren't really able to figure out where you are. To determine where you are, you take out your phone and start using the ARKit app. As you scan the room, you're able to detect all the walls around you. And just as you finish detecting the walls, you get a message that tells you almost exactly where you are in the building. That's pretty convenient, right? Just an app, a camera, and our algorithm. Okay, now I'll talk about the very first part of our solution. So GPS stops working when a person enters a building. However, we're still able to approximate where a user is by using their last known outdoor location. For example, we can assume that they haven't walked far after going through an entrance. Particle filtering can also help us determine a course localization, which is ignoring paths and locations that we can only get through by going through walls. In this image here, you can tell that as more time passes, particle filtering is able to filter out more areas that a person cannot be. Next, I'll move on to plane matching, which is the focus of our research this summer. In order to match planes around us, we need ARKit and uniform floor plans. ARKit will be used to detect vertical planes around us, and the floor plan will be used to match the planes too. The reasons we decided to go with plane matching to get an accurate positioning of a user is that both floor plans and ARKit are very accessible, and it costs less than many other methods that I previously mentioned because it doesn't need that previous mapping process. Before we move on to the next section, I'll give a quick summary of our methods. First, we conducted ARKit plane detection experiments in order to test its abilities. Next, we extracted the walls from our floor plan to generate a binary map. And lastly, we matched the ARKit planes and extracted walls with the rest. Okay, and Alex will be introducing the plane testing experiments.
So, through literature review, we found out there were no extensive assessments of ARKit's plane detection abilities in a realistic environment online. So we decided to test these through our own experiments. And we wanted to assess ARKit's ability to test planes from a variety of distances and different realistic environments for our system to work in the real world. So the first experiment we did was a basic static range experiment. And basically what we did was we stood from a wall and measured the distance, measured the furthest distance that ARKit could detect a plane before it was unable to detect it anymore. And we compared this using LiDAR-equipped phones and non-LiDAR-equipped phones. So what's LiDAR? The LiDAR stands for light detection and ranging. And what it does is that it emits laser pulses to create detailed point clouds. From these data in the point clouds, it accurately reconstructs the planes in 3D. So what we determined was that phones without LiDAR had a detection range of only about 3.5 meters on average, while phones with LiDAR increased that range from 1.5 to 2 meters to about 5 meters. We also decided to test the difference between LiDAR and non-LiDAR phones for their detection time and consistency. So we did the same static range experiment, and we just continued increasing the distance we were from the wall until we got to the maximum range. And as you can see in that graph over there, is one of our samples, is that the LiDAR phones had essentially a straight line where the times were not only quick but incredibly consistent, while phones without LiDAR were completely inconsistent, much slower, taking upwards of like 20 seconds sometimes, which didn't happen in this case, but happened in many cases, and yet. So also, we also conducted experiments with LiDAR-equipped phones to test AeroKit's plane detection algorithm, plane detection abilities when parts of the plane is blocked. Because in the real world, for example, if you look around you, not all the planes are visible here. So what we did was we tested one blue wall and one white wall. The blue wall is distance from 1 meter, the white wall is 1.1 meters. And what we did was we continuously covered the wall of objects until up to 75%. And then we tested AeroKit's ability to detect those walls. And for the white wall, this experiment caused an issue for us because we noticed that the lack of color and texture on this white wall meant that AeroKit could fail to detect almost everything past like 20%, which is pretty bad. And however, for the blue wall, we noticed that because the blue wall had texture and obviously a color, AeroKit was almost able to consistently detect the plane up to the maximum 75% cover, as you can see here, all around 0.7 seconds. And what we noticed from this was that white walls, which are very common in indoor locations, would pose a problem, so we had to find an issue to deal with this. Find a solution to deal with this, my bad. So we also did an experiment for static and dynamic detection. So basically, as you can see in these pictures, a static detection is basically what we did before. We stand still, have your phone, and a little movement, and see if AeroKit can detect the wall or not from different distances. Well, dynamic detection basically is, as you can see in the picture, Triton is walking, and the walking movement is what we tested to see if this would improve the AeroKit's plane detection on these white hard to detect walls. So, we tested this with only non-LiDAR phones, as by this time we knew that LiDAR phones could accurately detect walls and planes at an incredibly accurate and consistent time. So we found that even while moving, non-LiDAR phones could detect these basically impossible and hard to detect white walls at incredibly fast speeds at like 1.6 seconds on average for iPhone XS and 1.9 seconds on average for iPhone 11. While stationary, and this is actually better than expected, it was able to detect it in around average of 12.4 seconds on average for static detection and 16.3 seconds on average for iPhone 11 for static detection. And this basically fixed the issue of white walls being impossible to detect, as a user can simply walk around the room and AeroKit will be able to accurately detect these walls. So finally, we assessed AeroKit's plane detection ability in a medium 12 by 12 classroom, as well as a large room in the McHenry library. So first of all, the 12 by 12 classroom was just a normal classroom. It was like tables, desks, chairs, there was a TV, a whiteboard, and it was a realistic environment. And the reason we did this was we wanted to have information on whether static detection would be viable, the more convenient static detection would be viable for our system in these type of rooms, or if we would have to use dynamic detection for these type of rooms. So what we determined from this was that in a medium-sized room, AeroKit could detect enough planes to accurately localize our position, and although we could still do dynamic detection for better results. However, the large-sized room, what we noticed was that obviously the large space is very open, the range is only 5 meters. Only a few planes can be detected, and as you can see, these columns doesn't seem that far, but it's unable to be detected, meaning that we would have to use dynamic detection and more movements for successful localization. The logic also brought up the issue of angles. As you continue moving like farther and farther from a wall, the viewing angle of that wall is obviously changed, right? And then we were curious on whether does this angle really affect, how much does this angle, viewing angle affect AeroKit's plane detection ability? So what we determined was that there was no obvious effect from the angles of these, for the plane detection, and every single time it couldn't detect it, it wasn't because the angle was wrong, it was because the distance was too far away. In fact, even from almost 180-degree angle, we could accurately detect the plane. So here we have the experiment summary. Basically what happened was LiDAR increased detection by 1.5 to 2 meters, and it's also much more consistent and fast, much quicker than non-LiDAR equipped phones. And One of the big takeaways was the need for movement and dynamic detection for better and more robust plane detection results, especially for non-LiDAR phones. And this will also be needed in an open area for our system to accurately localize, or else we would be able to detect like no walls basically. And through a large number experiment, we also determined that distance was the biggest factor, and there's not an obvious effect of whether an angle had a result of this, had a cause of that. So next, Srijan will introduce the floor plan wall extraction process, as well as the ransack algorithm that we use to localize.
So the goal for our floor plan wall extraction was to solely obtain walls from any form of floor plan and create a binary map. And the criteria for the algorithm is that it should be able to quickly generate a series of binary maps given an input folder of images. So this is needed because our approach requires a map with only walls that the detected plane from the previously mentioned ARKit application will be put onto. And publicly available floor plans come in a wide array of formats, and if they're all consistent, then it'll ensure the user is localized accurately. And there are existing approaches for obtaining wall-only floor plans, such as creating them manually. However, this requires a large amount of time and some payment. Thus, the existing algorithm eliminates all costs of creating these floor plans and is much faster than other approaches. And these are a few examples of publicly available floor plans. Now, onto the floor plan model itself. We researched online to locate existing online models that can extract features from a floor plan. After extensive testing, we came upon a pre-trained online model which uses something called a convolutional neural network, which is short for CNN, and that accurately obtains features from a given floor plan. And in simple terms, a convolutional neural network is a type of computer algorithm that can be used in our case to analyze a floor plan image. And it consists of layers which apply multiple filters that detect specific features like edges and shapes. By learning these features, the CNN learns how to identify patterns in the image, such as walls. The model also outputs an image seen here with many detected features like walls, bedrooms, and closets. Almost all of the information in that image is not relevant to our current goals, as we only want the walls. So we filter through and select only the class that corresponds to walls to create an image of our liking. And then we apply some OpenCV functions to clean the image. And OpenCV is simply an image software library that aids in image processing. Finally, we output the resulting binary image comprised of walls from the input floor plan image. Now, the final step, as we have the planes from ARKit and the binary floor plan, now to accurately localize the user, we use something called a ransack algorithm. It stands for Random Sample Consensus, and it's an iterative algorithm that can estimate the best fit model of a set of data. In our case, the algorithm randomly samples 2 pairs of planes from all the detected floor plan and 2 pairs from the binary floor plan map. And then, after that, assumes they represent the same pair of planes and fits it to the detected floor plan. It then calculates the number of inliers, which are essentially overlapping planes, and it repeats the process. At the end, it chooses the result with the most number of inliers, which helps us accurately determine the user's location. And here you can see an example of our ransack algorithm in action. The first image represents the entire binary floor plan, and then after a first step of coarse localization and prior knowledge, we estimate possible locations of the user and narrow it down with the red circle. And then the image on the bottom left represents the detected planes from ARKit, and the ransack algorithm essentially fits these detected planes onto the filtered floor plan map to create our final result. Now for our results for ransack testing, we tested it and we found that it was successfully able to localize 1 out of 4 hallways, and it was able to match the entrance of a building. Now, a key point we noted was that it was less consistent in similar hallways, and we thought that this might be due to the fact that the algorithm faces difficulty in distinguishing between similar features of both hallways. Now on to our conclusion, which Hannah will be talking about.
Can you hear me okay?
Yeah, we can hear you, Emma.
Okay, so to summarize our research, we performed literature review on existing indoor localization methods, including the ARKit usage and plane matching methods. Also, we performed experiments to assess ARKit's ability to detect various colored and textured planes in different environments. So more specifically, we were able to find the maximum plane detection range for the ARKit, and the LiDAR was improved by the overall performance, especially in the planes with less features. And translational movement improved performance in the iPhones without LiDAR. Third, we incorporated and tested an existing code base to extract walls from floor plans of various appearances. And lastly, we implemented a ransack algorithm for plane matching and tested it with planes detected with ARKit. For some future contributions, we can develop a complete indoor localization system. We can complete the system by implementing the prior estimation, optimize the wall extraction algorithm, refine the ransack algorithm for better accuracy in a variety of environments, and create a navigation aspect for BVI people to traverse indoor setting.
And we believe this application, after further work, will immensely help BVI users to navigate through any indoor space after we develop a coherent indoor localization system.
And for our acknowledgements, we would like to share a special note of appreciation for our mentor, Patrick Chang, who guided us through our journey in SIP, and Professor Roberto, our faculty member. We would also like to express our sincere appreciation to Raja and the rest of the SIP team for making this research opportunity possible for us. Participating in this science internship program has been a privilege, and we are very grateful for the experiences and knowledge we gained from this program. Thank you.